Wouldn't it be cool to have a little black hole in your office? You know, maybe as a trash bin, or to move around the furniture, or just as a kind of nerdy toy. Why can we not make black holes? Or can we? If we could, what could we do with them? And what's a black hole laser? That's what we'll talk about today. Many thanks to our supporters on Patreon, especially those of you in Tier 4. We rely on your help to keep this channel going. And you too can help us on Patreon or check out the items in our gift store below this video. Everything has a gravitational pull, the Sun and Earth, but also you and I and every single molecule. You might think that it's the mass of the object that determines how strong the gravitational pull is, but this isn't quite correct. If you remember Newton's gravitational law, then sure, a higher mass means a higher gravitational pull. But a smaller radius also means a higher gravitational pull. So, if you hold the mass fixed and compress an object into a smaller and smaller radius, then the gravitational pull gets stronger. Eventually, it becomes so strong that not even light can escape. You've made a black hole. This happens when the mass is compressed inside a radius known as the Schwarzschild radius. Every object has a Schwarzschild radius, and you can calculate it from the mass. For the things around us, the Schwarzschild radius is much, much smaller than the actual radius. For example, the actual radius of Earth is about 6,000 kilometers, but the Schwarzschild radius is only about 9 millimeters. Your actual radius is maybe something like a meter, but your Schwarzschild radius is about 10 to the minus 24 meters. That's about 1 billion times smaller than a proton. And the Schwarzschild radius of an atom is about 10 to the minus 53 meters. That's even smaller than the Planck length, which is widely regarded to be the smallest possible length, though I personally think this is nonsense, but that's a different story. So the reason we can't just make a black hole is that the Schwarzschild radius of stuff we can handle is tiny, and it would take a lot of energy to compress matter sufficiently. It happens out there in the universe because if you have really huge amounts of matter with little internal pressure, like burned out stars, then gravity compresses it for you. But we can't do this ourselves down here on Earth. It's basically the same problem as making nuclear fusion work, just many orders of magnitude more difficult. But wait, Einstein said that mass is really a type of energy, and energy also has a gravitational pull. Yes, that guy again. Doesn't this mean if we want to create a black hole, we can just speed up particles to really high velocity so that they have a high energy and then bang them into each other? For example, with a really big collider? Indeed, we could do this, but even the biggest collider we have built so far, which is currently the Large Hadron Collider at CERN, is nowhere near reaching the required energy to make a black hole. Let's just put in the numbers. In the collisions at the LHC, we can reach energies about 10 TeV. That corresponds to a Schwarzschild radius of about 10 to the minus 50 meters. But the region in which the LHC compresses this energy is more like 10 to the minus 19 meters. We're far, far away from making a black hole. So why were people so worried 10 years ago that the LHC might create a black hole? This is only possible if gravity doesn't work the way Einstein said. If gravity, for whatever reason, would be much stronger on short distances than Einstein's theory predicts, then it'd become much easier to make black holes. And 10 years ago, the idea that gravity could indeed get stronger on very short distances was popular for a while. But there's no reason to think this is actually correct, and as you've noticed, the LHC didn't produce any black holes. Alright, so far it doesn't sound like you'll get your black hole trash can. But what if we build a much bigger collider? Yes, well, with current technology, it'd have to have a diameter about the size of the Milky Way. It's not going to happen. Something else we can do? We could try to focus a lot of lasers on a point. If we use the world's currently most powerful lasers and focus them on an area about 1 nanometer wide, we'd need about 10 to the 37 of those lasers. It's not strictly speaking impossible, but clearly it's not going to happen anytime soon. Okay, good. But what if we could make a black hole? What could we do with it? Well, surprise, there's a couple of problems. Black holes have a reputation for sucking stuff in, but actually, if they're small, the problem is the opposite. They throw stuff out. That stuff is Hawking radiation. Stephen Hawking discovered in the early 1970s that all black holes emit radiation due to quantum effects, so they lose mass and evaporate. The smaller the black holes, the hotter and the faster they evaporate. A black hole with a mass of about 100 kilograms would entirely evaporate in less than a nanosecond. Now, evaporation sounds rather innocent and might make you think of a puddle turning into water vapor. But for the black hole, it's far from innocent. If the black hole's temperature is high, the radiation is composed of all elementary particles, photons, electrons, quarks, and so on. It's really unhealthy, and a small black hole converts energy into a lot of those particles very quickly. This means a small black hole is basically a bomb. So it wouldn't quite work out the way it looks in the Simpsons clip. Rather than eating up the city, it'd blast it apart. But if you'd managed to make black holes with masses about 1 million tons, those would live a few years, so that'd make more sense. Hawking suggested to surround them with mirrors and use them to generate power. It'd be very climate-friendly too. Lewis Crane suggested putting such a medium-sized black hole in the focus of a half mirror and using its radiation to propel a spaceship. Slight problem with this is that you can't touch black holes, so there's nothing to hold them with. A black hole isn't really anything, it's just strongly curved space. They can be electrically charged, but since they radiate, they'll shed their electric charge quickly, and then they are neutral again, and electric fields won't hold them. So some engineering challenges that remain to be solved. What if we don't make a black hole, but just use one that's out there? Are those good for anything? The astrophysical black holes which we know exist are very heavy. This means their Hawking temperature is very small, so small indeed that we can't measure it, as I just explained in a recent video. But if we could reach such a black hole, it might be useful for something else. Roger Penrose already pointed out in the early 1970s that it's possible to extract energy from a big spinning black hole by throwing an object just past it. This slows down the black hole by a tiny bit but speeds up the object you've thrown. So energy is conserved in total, but you get something out of it. It's a little like a swing by that's used in spaceflight to speed up space missions by using a path that goes by near a planet. And that too can be used to build a bomb. This was pointed out in 1972 in a letter to Nature by Press and Teukolsky. They said, look, we take the black hole, surround it with mirrors, and then we send in a laser beam just past the black hole. That gets bent around and comes back with a somewhat higher energy, like Penrose said. But then it bounces off the mirror, goes around the black hole again, gains a little more energy, and so on. This exponentially increases the energy in the laser light until the whole thing blasts apart. Okay, so now that we've talked about blowing things up with bombs that we can't actually build, let us talk about something that we can actually build, which is called an analog black hole. The word analog refers to analogy and not to the opposite of digital. Analog black holes are simulations of black holes in fluids or solids where you can trap some kind of radiation. In some cases, what you trap are sound waves. I should add here that sound waves in physics don't necessarily have something to do with what you can hear. They are just periodic density changes, like the sound you can hear, but not necessarily something your ears can detect. You can trap sound waves in a similar way to how a black hole traps light. This can happen if a fluid flows faster than the sound speed in that fluid. You see, in this case, there's some region from within which the sound waves can't escape. Those fluids aren't really black holes, of course. They don't actually trap light, but they affect sound very much like real black holes affect light. If you want to observe Hawking radiation in such fluids, they need to have quantum properties, so in practice one uses superfluids. Another way to create a black hole analog is with solids, in which the speed of light changes from one place to another. And those analog black holes can be used to amplify radiation too. It works a little differently than the amplification we already discussed because one needs two horizons, but the outcome is pretty much the same. You send in radiation with some energy and get out radiation with more energy. Of course, the total energy is conserved. You take the extra from the background field, which is the analogy for the black hole. This radiation which you amplify isn't necessarily light. As I said, it could be sound waves, but it's an amplified, stimulated emission, which is why this is called a black hole laser. Black hole lasers aren't just a theoretical speculation. It's reasonably well confirmed that analog black holes actually act much like real black holes and do indeed emit Hawking radiation. And there have been claims that black hole lasing has been observed as well. It has remained somewhat controversial exactly what the experiment measured, but either way, it shows that black hole lasers are within experimental reach. They're basically a new method to amplify radiation. This isn't going to result in new technology in the near future, but it serves to show that speculations about what we could do with black holes aren't as far removed from reality as you may have thought. This video was sponsored by my friend and colleague, the astrophysicist Brian Keating. Brian has his own YouTube channel and podcast called Into the Impossible. You may have seen him on Lex Fridman's show. He's done a lot of interviews with big thinkers, including Nobel Prize winners like Sir Roger Penrose and Reinhard Genzel, and other luminaries like Shep Doeleman, leader of the Event Horizon Telescope project. Brian is an experimentalist who built some of the most sophisticated cosmology telescopes on Earth and space. He's great at explaining the tricky physics behind exotic phenomena such as birefringence or sterile neutrinos, and he offers his opinions on some of the more speculative ideas that are floating around in physics. For example, wormholes, the multiverse, or conformal cyclic cosmology. I find his channel both educational and entertaining, and it's always worth checking out what he's been up to. If you're interested in what I talk about on my channel, it's very likely you'll also enjoy the experimental perspective Brian's channel brings. Link to his channel is in the info below. Thanks for watching. See you next week.